constructing non-parametric regression estimators, it doesn't really matter whether we assume the inputs are fixed or random for the most part. We'll construct them in the exact same way. It does matter when we do theory, though. Not all theoretical statements are going to be the same, actually, between the fixed and the random worlds. There are some kind of subtle differences that make it pretty interesting. I can point out that in the list of references I gave you, this book called, well, Larry will know the name of the book. I actually forget it, but the authors are Gyorfi, Kohler, Krizak, and Volk, or Volk, depending on how you pronounce that. They assume random inputs, okay, and they actually kind of give an argument for why that's the most natural setup. If you look at the Sibikoff book, then he assumes fixed inputs. They can't actually prove the same thing between the fixed and the random worlds. And the book by Gyorfi and the other authors actually talk about how there are some questions that in the random world are kind of left open. So when I talk about theoretical statements the next couple of lectures, I'm going to mix and match. I'll tell you some for random inputs and some for fixed, just to kind of give you an idea of what's out there. But keep that in mind that they're not always the same. Even though we may actually implement in practice these estimators in the same way, we can't exactly describe the theoretical performance in the exact same way. Okay, so last thing is that right, so these inputs can be in d-dimensional space. That's the most general setup. After I talk about k-nearest neighbors really briefly, I'm going to assume that d is 1 for the rest of the methods. So I'm going to talk about univariate non-parametric regression. I'm not doing that because that's the only way to describe these methods. All the methods I talk about actually have multivariate extensions. At the end, we'll talk briefly about them. But it's just easier to see all the concepts in the univariate case. And we'll get to high dimensions at the very end of the sequence. All right, so the plan after just reviewing k-nearest neighbors is to talk about, I think, maybe somewhat ambitious. Talk about kernel smoothing and local polynomials. Then talk about splines and smoothing splines. Then I'm going to talk a bit about, this is over the next couple of lectures, reproducing kernel Hilbert spaces. I'm going to kind of talk a bit about what we call the class of linear smoothers, maybe talk a bit about wavelets and adaptive methods, and then we'll talk about the high-dimensional case. That's a lot of stuff to talk about. I think I'm going to do kernels and local polynomials pretty quickly since we've already seen kernel density estimation. I'm going to spend more time on splines because we haven't seen that yet. So if anybody is dying to see something that I went over quickly, speak up. Maybe we can spend more time on one thing versus another. If you guys are terribly bored by splines, then I may kind of speed up on that section. So I don't know, I guess it's flexible. All right, so what we saw is the kind of straw man at the end of the last lecture was this k-nearest neighbors regression. Okay, so the way we construct this estimator, given these xi and yi pairs, is that we just given some value k, the number of neighbors, so it has to be bigger than 1, or bigger than or equal to 1. We're going to average over all points xi, or I guess I'll write I, that are one of the k-nearest neighbors to x. So when I is in this set n sub k at x, it means that xi is one of x's k-nearest neighbors among all the points x1 through xn. We take their y values and we just average them. Right, so these might be my input x's. And let's suppose that k was 3. So you give me a new x, let's suppose it sits here. So I just find the k nearest neighbors. So 3, I find the 3 nearest neighbors. in my data set to this input point x. I take their yi values, right? So think of some, if these are the input points, think of some curve coming out of the board. I take the height of that curve over these three values, and I average it. And that's what I predict at x. That's all the k-nearest neighbors is doing. Okay, so it's very simple. It's just like a local averaging, where the local neighborhoods are defined by kind of the geometry of these input points x. Okay, so it's actually, I mean, we can see it right here, but I can also write this as the sum over all I equals 1 to n, of wi of x times yi, where these weights are either 0 or 1 over k. Picks up whether or not point I is one of the k nearest neighbors to x. And so I like this representation because it's telling us that the predictions, f hat, are just linear combinations of the y's. These weights depend on x, okay, but they don't depend on y. I can always write this as just sum of wi yi. Okay, so this is an example of what we call a linear smoother because of this representation. And this class is maybe way bigger than you think. We're going to come back to that a lot. So k-nearest neighbors, it works pretty well. I don't want to dump on it as if it's a bad method, but it's never going to give us a very smooth fit, right? Because it's always performing a discrete averaging. Points are either in or out. These weights aren't smooth. So in some sense, it's kind of unnecessarily jagged, right? Because when k is very small, we want to regularize the bits. We want something that's actually not moving too much. It still will just be discrete levels that we're taking the average over. It's not going to be smooth. And when k is small, so we want to make the fit more adaptive, it tends to be very, very jagged, right? Because those local neighborhoods will change a lot as we move around this input point x. We want to make the prediction. Okay, so still, it has some nice properties. So I'll just kind of give two nice properties. And like I said, we're going to be talking about all this stuff pretty quickly. So just try to pick up maybe the main points of these properties. And we're not going to focus too much on the details, but if you're curious, I can always give you references for this kind of stuff. So if we assume the random input model up there, so f0 is the conditional expectation of y given x, then under this random input model, if we take k equals k of n, so we take a sequence of problems where we're going to change our choice of k with n, right? That's a pretty critical choice because if k is too small, we may be overfitting. If k is too large, we may be underfitting. Right? There's a trade-off there in how adaptive the method is. But if I take k to be the sequence of choices of neighborhood sizes k of n that satisfies the following properties, it goes to infinity. As n goes to infinity, but k n over n goes to 0 as n goes to infinity. So it goes to infinity, but not as fast as n. So for example, I can take kn equals root n. That's a perfectly fine choice. Then under this choice of k, and some very, very weak assumptions on the errors from that model, we don't actually even need independence of the errors and x's. We get that this constructed regression function f hat is consistent. So it means that in some sense it converges to f0. And here's what the statement is. It's that if I draw a random x from that model, and I ask for the value of f naught of x, the true regression function, the difference between f hat of x and that, and I look at the distance between these two. Right, so I guess this is actually just, there's no norm needed. Then the expected value of this goes to 0. Okay, so under a random draw from this input model, if I look at the norm as the expected value of the difference of the functions at a random input, it goes to 0. So it's consistent. F hat is consistent for estimating f naught in this sense. Okay, and even more than that, if assuming that F0 is Lipschitz, remember what Lipschitz is? How many people remember what Lipschitz continuous is? Okay, so I'll just repeat it. Maybe not everybody remembers. It means that if I have any 2 points in the input space, say x and z, I need to have the distance between f mod of x and f mod of z being less than or equal to L times the distance between x and z. This has to hold for all x and z. So I have to say that there exists some L, right? There exists some L such that this is true. Okay, so that's the definition of Lipschitz. It means that the difference in outputs is never more than L times the difference in inputs. So let's just actually have a quick check here. Is this function Lipschitz? This piecewise constant function? So this is it's just one it's a function of one variable. Maybe this is x, and attains different levels. Is that a Lipschitz function? Why is it not Lipschitz? Yeah.
Isn't it Lipschitz in the sense that, like, if you pick L to be larger than the maximum f and the minimum f, then the difference between f of x and x will be lower than x max?
No, not quite. Yeah.
The distance between x and z is unbounded for x and z. So you can't shoot an L large enough to cover all these.
Okay, so I'll just say that, let's say that I'm going to restrict the domain of this function to an interval a, b. So is it Lipschitz on that interval?
First order differential is not bounded.
So where is it not bounded?
At the distinct point.
Yeah, right. So here, I could take x and z arbitrarily close. I can move them to 0. I can move their difference to 0, right? If I take them just on either side of this boundary. But the jump in f between a point here and a point here is the same. Let's just say it's 1. So the difference between these two heights is 1. So it's never going to be it's never going to be less than or equal to some constant multiple L for some fixed number L times the distance between x and z. Because if you give me any L, then that works. I'll just take x and z close enough to break it. Right, to make x and z so small that when I multiply it by your L, it's smaller than 1. Okay, so this is not a Lipschitz function. You can't have jumps like this. So for example, in this statement I'm about to make for k-nearest neighbors regression, it's saying that the true regression function cannot jump like this. Okay, we're only getting convergence rates for functions that don't have this jumpiness, that are smoother than this in some sense. So if F0 is Lipschitz, then we can further say that this same quantity here goes to 0 at a certain rate. So it's O of n to the minus, I think it's 2 over 2 plus d. Okay, so let's take d equals 1. It goes to the 0 at the rate n to the minus 2/3. Remember, we're doing non-parametric regression, so parametric rates are like 1 over n. I guess it should be squared. Okay, so it's not great, but it's not a terrible convergence rate. What happens if you take d bigger and bigger? This gets slower and slower, right? When d is, say, 5, this is like n to the minus 2 over 7. Okay, so actually pretty slow convergence to the true function, and we can't handle functions like this. We can't handle these, functions like this, these jumpy functions. Yeah, my question.
I'm guessing even if you assume a strong smoothness condition, you can't get a linearity.
In a sense, that's right, yeah. So with k-nearest neighbors, if we up the smoothness of f, we don't really get better rates. That's part of the reason why we're going to kind of progress past it. Because it's so, it gives such jagged rates. All right, so the next thing we'll talk about after we kind of blitz through k-nearest neighbors regression is kernel smoothing. I guess Larry brought up a good point, which is that we have two types of kernels that are related, kind of that we're talking about. I'll always say kernel smoothing to mean this type. When we talk about reproducing kernel helper spaces, I'll try to say RKHS, or call them Mercer kernels, which is not a bad terminology for them. So we're going to move from discrete averages essentially to smooth averages. That's all we're going to do. It's really going to be the same story. And I'll just assume D is 1 for simplicity. So we're going to start with a kernel function K. Okay, it's going to have, so it's going to be a function from R to R. Generally, it'll be a function from RD to R, right, for some D. And it's going to have a few properties. I think we might have already written these down, but I'll just write them down for completeness. It has to integrate to 1. We have to have the integral of x, k of x dx is 0. And the third property is that the integral of x squared, k of x dx, is bigger than 0, and it's also finite. We're going to make this be finite also. Okay, so we can think about k as a probability density function, right, of something that has mean 0, for example, and this would be its variance. And some common examples are the Gaussian kernel. This is like the Gaussian kernel. That's the one I always think about just because it's easy to remember. Many other choices, but just think of that one in case you're forgetting what kind of kernels we have. So once we have this set up, we're going to choose another parameter, which is called a bandwidth. Okay, so there's another parameter we're going to play with, and that's the bandwidth. This is a number of h. So this just acts like k in k nearest neighbors regression. It allows us to adjust the flexibility of our estimator. Right? For k nearest neighbors regression, for small k it was very adaptive. For large k it's not so adaptive. It's going to be the same thing here. For a large value of the bandwidth, it's not so adaptive. Or I'll say flexible. I'll reserve the word adaptive, which means something else. It's not so flexible. And for a small value of the bandwidth, it's very flexible. And so after we have this set up, we're going to now define the kernel smoothing estimator in the following way. So you give me an input point x. I'm just going to take a sum over all input points I that I've observed, and I will I'll look at the weight that my kernel assigns to point x when it's centered around xi, and I adjust for its width by this bandwidth h. I'll draw a picture in a second. Times yi, and I just want to normalize by dividing by the sum over all j of k of x minus xj over h. That's the kernel smoothing estimator. Okay, I can also write that as wi x times yi. Also just the linear function of the points yi, where this wi is this way here. Right? It's just k of x minus xi over h divided by the sum of all of these. Alright, so let's just kind of an analogy between k nearest neighbors and kernel smoothing. Well, first of all, they're both linear functions of the data, of the output, yi. And in both cases, the weights sum to 1. Right? Across all i's, these weights sum to 1. let's now just draw the univariate case. So let's suppose I'm just drawing latches down here for my input points that I observe xi. Let's suppose that the output points look something like this. And I say I want to make a prediction here. X. So what kernel smoothing is going to do is it's going to take x, and essentially I'm going to think about drawing a little kernel state around x of a certain shape, and that shape has to do with my choice of k and also my choice of advanced kernel. It may look like this. Okay, then I'm going to evaluate this curve at each input point x. That's going to give me some value of the weight here. I'm going to multiply that weight by the value of the corresponding output point yi. I'm going to perform that weighted average. So it's like a smooth average of the output points, where the weights are determined by the proximity of x to my input points xi. K-nearest neighbor progression is actually just going to grab a handful of those. Like if I do 4 nearest neighbor progression, it would grab 4 and average their outputs, regardless of how far anyone is individually close to this x. And it's also discrete. So sometimes it seems like we have an advantage of using kernels because of this smoothness, right? We're actually taking into account, in a sense, a lot more of the training set when we're doing kernel regression. And well, so I guess I'll skip to telling you the theoretical punchline with kernels, and then we'll kind of continue with more of the methodological approach. So, right, for kernels, if I assume that go back to the same statement here. If I assume that not f0 is Lipschitz, but its derivative is Lipschitz. So if I assume that f is has a Lipschitz derivative, so in a sense it's even smoother than this, then with kernels I get a rate that's n to the minus 4 over 4 plus 2. So a smoother function gives us a smoother rate. And the reason is because the kernel fits themselves are smooth. And the smoother the function, the smoother the fit. However, with k-nearest neighbor regression, they're always jagged, so they can't really adapt to a higher level of smoothness. I'm also going to describe for you a method in just after kernels that if I assume that not f is Lipschitz or f prime is Lipschitz, but if the kth derivative of f is Lipschitz, so if f has k derivatives and the kth derivative is Lipschitz, then we're going to get a rate that looks like 2k over 2k plus d. Okay, so it's like every time I assume more smoothness, I can actually map that smoothness to my estimator, both practically speaking and also in terms of how fast I converge to the true function. Okay, so that's the kind of punchline with kernels. Any questions? Yeah.
So when you describe kernel smoothing here, you said the kernel is centered at the observation point.
Yeah.
But on the surrogate vector, you shouldn't have centered at xi because my observation point is x, right, f of x. So, and my kernel of k of x on the tracking xi is like I'm centering it at xi.
I mean, you can really think about it in either way, right? Because think about a normal distribution. I can think of, first of all, the kernel's symmetric. I mean, that's not a property I actually wrote explicitly, but this one is symmetric, right? K of x is k of minus x. So I could write xi minus x or x minus xi, it's the same thing. Most choices of kernels are symmetric. Actually, that's really what this property is saying, but it's just a little less strict. So I can think about centering it at x, for example, and then evaluating at x line.
I think the kernel functions come from density functions. So is it necessary to assume the integral of x squared bigger than 0?
It's not always true that they come from density functions. I mean, it's often the case, but I think Larry has a bunch written down in his notes on kernel density estimation. You can look at them. They're actually not, they don't usually correspond to probability density functions for random variables that we're familiar with. We assume that this is the case because otherwise we wouldn't be able to. So I'm not going to go through the proof to this, but when you go through the proof to this, we do a Taylor expansion essentially. And if we don't have that this thing is finite, then we can't conclude that we have the proper rate. So if it's, I mean, it's generally going to be positive, but if it's infinite, we choose kind of a degenerate kernel, then we don't get the right result. This is very rare that you're going to write down a kernel that can satisfy this is true. But just to be precise, we're going to want to include that statement.
Were you worried about infinite or zero?
I mean, maybe we should add smaller than infinity.
Oh,
Yeah, I think that's what I said in words, but you can put it here if you like. Okay, so we spoke about kind of the good thing about kernels. I'm going to go to, I mean, it depends what we want to call kernels. I'm going to call the next thing local polynomials. It still is a kernel estimator. We're just doing something a little different. When I talked about that rate, I was actually talking about kernels and local polynomials all together because they all still use this kernel function. This one right here. But as we've written it, there's a shortcoming of this estimator f hat. Let's see if I can get you to guess it by drawing a picture. Okay, so let's suppose we observe data on this interval. I'll just draw lines again for the input points x, my x i's. Let's suppose we want to make a prediction here. That's the value of x we want to make our prediction at. What's going to happen here with our fitted prediction? This is our entire data set. There's going to be a problem with it.
Is it biased towards the values closer to the center because there's nothing on the opposite side?
Right, yeah. So the weights are kind of asymmetric. We don't have weights on this side. So we're picking up all the weights on this side. Now what's going to happen with our fitted function, the estimate there, based on this picture? What tendency do the points to the right have?
Slightly higher.
Yeah, it's going to be too high. So we're going to have a bias, actually. The kernel regression fit might look like that. So kernels, as written down there, they suffer from bias at the boundaries. Kind of a well-known problem. Because of the weights being asymmetric. We're averaging the y values, but we're looking at a set here of y values that are to the right. We have more weights than the points to the right. We don't have as many points to the left. So the estimated function is too high here. So there's kind of two ways to fix this. The first is that people have done kind of extensive calculations, these asymptotic calculations for correcting the bias. So we can work out the bias under some assumptions. We try to make that asymptotic correction in a finite sample. In my experience, or my opinion, that doesn't tend to work as well. Okay, and there's a lot you need to assume to make that correction valid. It's also hard. There's an easier way to fix it, And that's to kind of go up in order in terms of the order of estimation here. We're going to use what's called a local linear fit. So think about kernels as a local constant fit, and we're going to go up to a local linear fit. And how I'll motivate that is like this. Let's suppose we want to make our prediction f hat of x, and I'll call that just theta hat. Okay, I claim that theta minimizes the following criterion. Overall theta, I'm going to look at look at all values theta, and I look at this kind of weighted regression problem where I'm just choosing one parameter theta to minimize the weighted sum of squares of yi to theta. The answer I get is exactly this. It's theta hat equals this big term right here. It's exactly the kernel regression. So theta hat depends on x, so we're solving a different kind of constant regression problem at every x. So when we write it like this, by the way, do you guys believe this? This is a smooth problem, so if I wanted to find its minimum over theta, I could just differentiate it and set it equal to 0. And when you do that, you'll see that theta hat is just exactly that expression. It's a weighted average of the y's for those with the weights. Right, if the weights were all 1, then I just get then theta is obviously going to be the average of the y's by far. But because of these weights being here, it ends up being that. So when I write it like this, you may ask yourself, well, why don't I make my estimator even more adaptive, even more flexible? I'll use the local linear fit. It's still kind of a kernel method, so I'm going to use this kernel. But I'm going to model f at x as, I'll write it now as beta 0 plus beta 1 at times x. And just remember that these coefficients here, beta hat and beta 1, they're going to depend on x. I'm going to solve a separate problem for every input point that I want to make a prediction at x. Just like here, I find a different constant value theta for every x. And I'll just do the same thing. I'll minimize over all beta 0 and beta 1 this criterion where I take the kernel weights k of x xi minus x over h times yi minus beta 0 minus beta 1 squared. So if we go back to this problem, it's like instead of making average, we're actually going to fit a linear function of x at every point. And then we're going to evaluate that linear function at our input point x, and that's going to be our prediction. So the advantage of this method is that it actually eliminates the bias in kernel regression by a huge margin in practice. So we get rid of this boundary bias issue a lot in practice. We're much better off at predicting the boundaries. And in fact, we can go through a Taylor series argument to show that we get rid of the bias to first order exactly in finite sample. It's a very kind of simple argument. We both do it. See how Okay, so the first thing I want to do is I'm going to write, I claim that I can still, like I could in the last two cases, I can write this as a yi's, some weighted function of the yi's. So why is that true? At kind of a high level, it's true because at every x, I'm just performing a weighted regression. Regression is a linear function, so I can at the end just kind of rewrite it to look like this. There's nothing nonlinear in the pipeline. It's all linear as a function of the y's, right? Regression, I can always write the fitted value as the matrix times y. So to get there, we're going to solve this problem just with a better notation. I'm going to write b of x, use that notation to denote a vector that has a 1 in the first component and an x in the second component. Just when I evaluate at x, this gives me this vector. I'm going to make B an n by 2 matrix, capital D, that has all 1s in the first column and it has x1 through xn in the second column. There, in other words, the rows of B are given by just this guy, B of xi. And I'm going to choose omega to be this diagonal matrix, n by n diagonal matrix. And its entries are going to be evaluated. Its diagonal entries are just going to be the kernel weights at the input x's. Okay, and y is just going to be y is just y, the components of y, obviously. Okay, so that's just some notation. Let's bring us to the matrix world. And now we should be able just to, straight from our knowledge of linear regression, we're going to write down the solutions to this beta hat, not beta hat 1. Now I'm just recalling our formula from weighted least squares, which hopefully, if you've forgotten, you believe me that it's true. But if I didn't have the weight there, why don't we do that one first? If I didn't have these kernel weights, and these were all 1s, what would the optimal betas be in this notation if this D was this matrix? This is just like the design matrix, the predictor matrix in this regression. So what would the coefficients be here? Yeah, right. B transpose B inverse B transpose Y. Okay, so I've left a gap there on purpose. How do I fill in the gap now that I have this weight matrix? What goes there? It's just like, yeah, so this is just weighted least squares. Again, like I said, maybe it's believable now that we wrote down the usual regression equations. Those are just the coefficients, beta hat, not beta hat 1. So that's exactly the coefficients to solve this problem. Now how do I make a prediction at y? Remember, f hat of x was just beta naught hat plus beta 1 hat times x. I'm just going to write this as b of x transpose beta naught hat beta 1 hat. Right? B of x was just this guy 1 comma x. So clearly that's just the same thing. And then I'll just plug in for what beta hat and beta 1 are, and we'll see that I get b of x transpose b transpose omega b inverse b transpose omega y. Okay, so maybe it looks a bit messy, but what does it tell us? The fitted values are just a matrix, or in this case, sorry, a vector transpose X. Just some vector transpose X. Yeah, question.
So as a matrix, before Y still has a linear projection matrix.
Does this have the projection matrix?
Yeah.
Well, it's not quite a projection because a projection will need to have need to be symmetric, right? So I need to have something like omega b on the other side. These are the coefficients, but not the fitted values. But it's closely related to projection. You have a question? Okay, so we're actually going to use this to show now that the bias from local linear regression to first order is zero. It's a pretty simple proof, unless I mess it up. And you may want to pay attention to this because on your homework, we haven't released yet, but tentative question is for you to do a similar calculation, but for polynomial regression, to show that the bias is zero to the kth order. All right, so I'm going to claim two properties first about, I'm going to call this, by the way, Wi. I'll call this W of X. That's just some vector W, X transpose Y. And so this is like I said. So it's just a weighted combination of the y's. So these are the weights here. They're defined by that vector. I'm going to claim some properties about these weights. And then we'll use them to prove something. The first is I claim that they sum to 1. Again, so you have a monster property. Remember, this was true in K nearest neighbors because the weights were all 1 over K, and there's K with a non-zero point. And it's true in kernel regression. I erased it. But it's because we normalized. It was kind of obviously true because we always normalize by the sum of the kernel weights. It's still true here. We haven't done anything different with respect to that property. And then we have this
Ryan, is that W of X I?
Wi of X.
Is that the same as W of X I? I'm just looking at the way you define W.
Good question. No, it's not. Maybe I should compare that to the property we talked about before.
Oh, right, I see. At each X you're saying the weights.
Yeah.
The components of W. I see, yeah.
Sorry. Thank you for helping clarify. Yes. But I don't think I had, no, I had the same thing before. I called it Wi of X, Yi before. Right. So this property we still have, and then we have another property which makes local linear regression special. Not true for kernels. For kernel regression, I'd be about the first one. And that's xi minus x times w of xi equals 0. So that's true for any x. So the proof of these is very simple, but it's maybe not so obvious to see. Let's see if I can remember it. So, right, so as I've defined it, this is equal to the sum of Wi of x, yi, right? to okay, so now I'm going to multiply this. So this is true for any z, right? So I define the bit. So I'm going to choose in particular z equals b times the vector. So I'm going to actually do b times, doesn't really matter what I call it, I guess. Call the vector c. Okay, so what's going to happen though is that I'm going to be able to read off of, depending on how I choose c, okay, this is going to cancel. I'm going to be able to read off of these weights straight from c and that b of x over there. Okay, so I think we just have to do this for a couple of different choices of c. The first is what happens if I choose c to be the vector 1, 0. Okay, then I get b of x transpose c. What's b of x transpose c? That's just 1, the number that just pulls out the first component of b of x, which is 1. B of x was 1 comma x, equals this sum of wi of x times b times c. Now c was just 1 comma 0, so this is going to pull out the first column of this B matrix. This is just going to be the vector of all ones. So now I get, from this choice, I can see immediately that the sum of wi of x is 1. Right? Because this side is the sum of wi of x, this side ends up just being the first component of b of x, which is 1. So I've just proved this first property. Question?
So if that's a prediction, can you constrain both B and C to be y? Because you written down, I think B, C should be y. Is that correct?
I just said that regardless of what y is, our prediction has this form. So it has to hold particular for, I mean, I think this is y if you want, it's fine. It has to have this form. So the same formula is going to hold when y is in particular equal to BC. I can't express every y in BC, but it holds for at least this particular choice of y.
So it's choosing your regression. Is that?
Yeah. Just to prove this. Okay, now I should be able to choose C in one other way to get this property. And I think it's probably going to have to be the case that it ends up being this one. So I can't quite remember, to be honest. We'll just work it out. So if I choose C to be 0, 1, then on this side I get x, right? Because I get B transpose 0, 1. Remember, this is, I'm forgetting, this is 1, x transpose. That's what this B is. So if I do this transpose C, then I just get x equals the sum of wi of x times b times c. B being that matrix, if I multiply by 0, 1, I just get the columns of the inputs. So I get that x equals the sum of wi of x times xi. Okay, now maybe y is potentially confusing people here. That should have been a yi. Sorry for the source of confusion. So I get x equals the sum of wi x times xi. But since the weight's on to 1, I can also say that that's true, right? There's no hurt doing that. There's write in the x so we're all clear. Wi of x times x equals this. And then just by rearranging, I get the second property here. All right, so those are both definitely true properties of the local linear fit. And now quickly sketch out for you why they're important. Okay, this next one's a very simple calculation. Let's just suppose we're interested in the expected value of our prediction at x. All right, that's just the, it's going to be the expected value is a particular weighted sum. And now I'm going to, like I said, I'll mix and match. I'm in a world now where I'm going to consider the inputs fixed. So x1 and x on are fixed. And only y is random. Okay, that's the world we're considering for the statement. So this expectation is only over y. So it's the sum of wi of x times the expected value of yi. Yi was f naught of x naught, f naught of xi plus error. The error had mean 0, so it's just f naught of xi. Right, the bias, by the way, is going to be the expected value of f naught of x minus f naught of x. That's the bias. So we're going to want to make this equal to f naught of x. So we're going to do a Taylor expansion now of this function around the point x. So through that Taylor expansion we get f naught of x plus f naught prime of x times x minus xi plus r. And this r has, it contains higher order terms, right? X minus xi squared over 2 times the second derivative, and so on. So I'm going to neglect that being sloppy, just we'll keep it as r. And we can see immediately, let's look at this expression. What do we get? Well, we get the sum of wi of x times f naught of x. But the sum of the wi's is 1, right? And this isn't dependent on I, so we just get, it's f naught of x. That's great, so we want it to be. Now we don't want any more terms, to be honest, because right, we want this to be exactly equal to this. So what do we get from the second term? We get that this is f naught prime of x. I'll pull that out, it doesn't depend on I, times the sum of wi of x times x minus xi. But we just proved that property. Look, this whole term is 0. So actually, it doesn't have any bias to first order. We just look at a linear approximation of the function plus r. So for kernels, this isn't 0, and this is what you're seeing actually. That's why it's shifted up its boundaries. But for local linear bits, that's not the case. So the bias is only second order higher. Okay, let's take a break. You can ponder about whether that calculation made sense or not. Take a couple minute break. Give me a new x that wasn't part of my sample. There's an undergraduate or master's level textbook that they release. It's a separate book. Trevor, my dad, and someone else here, that's not me. Is that what you mean? Yeah. Oh, by the second issue of the book. Yeah, All right, so I'll start off our tradition today by telling you a joke. I also have a competitor email to me as a competitor, so we can even do the full voting thing. All right, so here's my joke. Remember, the rules are has to be about statistics and machine learning. And I'm also, this is a pretty bad joke. I'm going to start low. Maybe a little bit funnier next day. All right, so a physicist, a mathematician, and a statistician go hunting. And they all see a deer. So they're lined up to shoot it. And the physicist aims and takes his shot and ends up 10 feet to the left. And the mathematician aims and takes his shot and ends up 10 feet to the right. And the statistician throws up his arms and says, "We got it!" All right, so we have a joke now that was it's now competing with this one for the top role. I won't announce who it is, by the way, unless they win. So you can send me jokes, and if your joke doesn't fly, then you don't have to be embarrassed or ashamed. All right, so I hope I don't mess this up to the person who sent me the joke. Why are open source software packages the best? They just are. All right, so joke number one, joke number two. Should we do like a louder clap or just a hand raise?
I think a hand raise.
Hand raise, joke number one. Joke number two. Ooh, I think it's close, but I'm gonna maybe I'm biased. I think joke number one had a higher pattern. But the joke number two was the worthy competitor.
We need a scribe to keep writing them down so
Right, so I'm not coming up with a new joke for Thursday. If somebody wants to dethrone the hunting of statisticians and physicists and mathematicians, just send me an email.
Hey, the expectation there was respect.
That was more laughter than the joke. That doesn't count. That doesn't count for the
The expectation there was with respect to y, right?
Yeah.
Then why did you say that the expectation with respect to y of the errors is 0?
I mean the expectation, I can think about it in a couple of ways, right? I can think about my model being if you'd like to, think about only the errors or x being random. Okay, so in this model, the x is fixed, the errors are random, that's it. And the errors have expectation 0. So when I can move it for this part because even though these weights depend on xi, they're just fixed. Any other questions about
So you're saying that the randomness is in y is because of epsilon.
Yeah, right. So the way to think about this model for fixed x is that y is just produced. I mean, you can always think, if we want to, we can think about y as just the output of this model. So either x and epsilon are both random or just epsilon. So in this case, it's just epsilon. All right, so on your homework, unless our course staff naysays it as too hard or too long or something, we're going to have you prove essentially the analogy for this, but for local polynomial regression. Okay, so I'm not going to write down local polynomial regression. It's in the notes. I'm just going to tell you what it is. It's, okay, maybe I will write it down because otherwise it might be a little unfair to ask you a question about it. But it's entirely analogous to local linear regression. It's just that we make a polynomial fit at each input rather than a linear one. So for local polynomial regression, I fix some polynomial degree k, and then at x, I make this prediction. So make my prediction as a polynomial function of kth degree of x, where beta hat and beta 1 all the way through beta k minimize this criterion. Just our usual one, x minus xi minus x over h. Of yi minus beta 0 minus beta 1x minus beta k x k squared. Okay, so local linear is a special case with k equals 1. Kernel is a special case with k equals 0. When you work with this problem, it actually turns out to be the exact same reasoning we had to define these matrices, that it's still linear fit, so it still looks like this. Now we just get extra columns of B. That's essentially all it is that B has a column of x1 through xn squared, x1 through xn cubed, etc. This guy has 1 x squared all over xk, but everything else is the same. It's just, now it's the same formula. And what you can show is that those properties, where I had these properties like xi minus xw1 of x equals 0, that was the key property for local linear regression. For this guy, polynomial regression, it actually holds that this to the power of j is equal to 0 for all j between 1 and k. All those terms are 0. That's what you're going to prove on the homework. And as a result, you have a really good statement about the bias. You'll have to, hint to a Taylor expansion. It's very similar. What's the disadvantage to just keep increasing the polynomial order? If the bias looks better and better and better, like we're actually with local quadratic regression, for example, the boundary bias is already fixed by local linear regression. Local quadratic regression actually fixes bias in the interior of the intervals. And the bias just keeps getting better as we increase the polynomial order. Why don't we, in practice, just take like 10 to order polynomial? Yeah.
Computationally, that sounds terrible.
Yeah, that's one reason. It's not a bad reason. I mean, still, if I change this from like 2 to 10, it's not a huge deal. It's not like it's scaling with n. Bias variance trade-off, right, yeah, so as I make k bigger, I'm almost talking about the bias, right? Mean squared error is bias plus variance. The bias is going to get really good. The variance is going to blow up. It gets much, much larger. So overall, we're not going to necessarily predict that. Now, an extremely rough rule of thumb is that local linear regression corrects for bad bias boundaries. Local quadratic regression corrects for interior bias when the function has changing inflection points. Like it maybe goes from convex to concave. And so it tends to be a good trade-off. It's very heuristic to use k equals 1 or 2. And after that, it's not really worth it. But that's the answer. This is heuristic. It really depends on the problem. But just be aware of the trend.
Is there a theoretical reason for that? Like, is there a concrete reason, or is that an experimental, empirical?
For the variance getting bigger?
No, for the case that you said that quadratic is better for inflection function.
Yeah, I mean, you can do a similar calculation to the one I did. Essentially. And also, remember we kind of reasoned by drawing a picture that the kernel weights are asymmetric. It's similar with the linear versus quadratic case. In terms of the variance, there's also a question on your homework that asks you to support the idea that the variance gets bigger as k increases. Now we said you could either write down a theoretical calculation or do it by simulation. Just like try it on some data and show that the variance is bigger. Since we want you to estimate the variance, you're going to have to actually take that back. You don't need to use simulation. If you use real data, you just need to repeat it 20 times with maybe different subsets of data.
So you could like usually you could treat this as some optimization game where you want to choose, reach out a polynomial what to this on, so that you could control both the bias and the variance. How does this what does the rate look like in high dimensions? So because in high dimensions it looks like you have to take into account many polynomial terms in order to make it.
Yeah, good question. So the bias and the variance, I think we could, I'll just tell you the answers. So the bias looks like, essentially, it's going to look like h to the k times d. And the variance is going to be like 1 over nh under some assumptions. This again comes from Taylor series. Basically, everything about kernels you use Taylor series in the arguments. And then that's the reason why there's a very particular function class with respect to which we make all the statements for kernel regression. This all comes from Taylor series. So I have some of my notes. You can also look at the references in my notes. There's like specific references to the Sibikoff textbook. He does this all in great detail. But those are the point-wise bias and variance. They basically look like that. And so the rates we get for kernel regression, if we choose h appropriately, are as follows. But then I guess this will just be the punchline for today because we're almost out of time. So we end up going a little slower with kernels than I expected, but maybe I think it was a good thing. People were interested. We'll just find next time. So I'm just going to define, just like Larry did for density estimation, sigma KL to be the class of all functions. So this contains functions x0 such that I think I have a typo in the notes. Thanks for Jisoo to point that out. I have two typos actually, so I'll fix it after today, but you can look at Larry's notes or just pay attention to the board. These functions are also called f. They're k minus 1 times differentiable. So it's 1 less than this index here. And their k minus first derivative is Lipschitz. that's the function class I'm considering. It's usually called the holder function class. And like I said, the reason why people make statements about kernels with respect to this function class is because it's easier to use this function class mathematically for kernels after making the other expansion. There are kind of more or less equivalent function classes that, so for example, when we talk about splines, I don't know how much time we'll talk about rates, but all the rates for splines are not with respect to these ones, they're with respect to what we call Sobolev spaces. Basically similar. I mean, they're a little bit more broad, but they're very similar. So why a different function class? It's because it's when we do analysis with splines, we use different mathematical arguments, and with respect to those arguments, it's actually easier to use Sobolev spaces. Here, it's very natural to use the holder function spaces. So just bear in mind that the difference between these results that you'll find in the literature are often just due to ease of use. Like it's easier to use this function class with kernels. So here's a result, another convergence result. So we'll just take the univariate case like I said, but I'll show you what the D is going to come in. If that's my assumption on the true functions, if I have fixed input points, so I'm assuming them fixed and arbitrary, then the bias basically looks like 1 over, the bias, so expected value of, at any fixed point, x. Maybe I'll talk about squared bias. This is the squared bias is less than or equal to a constant times n or h to the let me make sure I get that wrong. K. And the variance is at a fixed point x is less than or equal to another constant times 1 over n times h. H is the bandwidth. K is the order of the polynomial that we're using for our local polynomial regression. This, by the way, this comes from Taylor series. It's actually mimics very closely the arguments we made for density estimation in Larry's lecture. And so then the mean squared error is less than or equal to the sum of these two. And if I want to optimize over the choice of bandwidth, looks like the best bandwidth to minimize the sum of these two is something like, I can just take a derivative with respect to h instead of equal to 0, there's sum, right? Ends up looking like minus 1 over 2k plus 1. So I use the theta notation, by the way, say that h is on the order of this. So both upper bounded and lower bounded by this rate. And then it turns out that the convergence rate, or the mean squared error, right, so the expected value of f out of x minus f naught of x squared is on the order of, after I stick in that value of h here and add these together, we get the rate n to the minus 2k over 2k plus 1. Now, if I were in higher dimensions, that one would be d.
Question? Yeah, just quick question. So how come the variance doesn't depend on k? Because you just said that the variance goes up when you increase k.
Yeah, question. So it kind of does in the sense that we're going to have to adjust the variance based on the bandwidth. So, the adjusting the bandwidth is going to affect the variance. Like you can see that at optimum, if I choose this for my value of h, then both of these are going to depend on k. I'll have this being equal to n to the minus k over 2k plus 1, this is equal to this minus, or 1 minus this, n to the 1 minus this. So at optimum, they both do depend on k. So it's just that the bandwidth we choose for local polynomial regression is going to kind of change as a function of k. So it's just kind of hidden in here.
I'm just concerned that there's a 2k in the denominator, so I'm wondering that should be
Here?
the variance should be in h
So you think about the bandwidth that you have to use for local quadratic regression being different than that for local linear regression. So it really is kind of hidden here. And this is what it's telling us, right? At least theoretically. Just know it. Good question, though. So anyways, that's the convergence rate. And like I said, for higher dimensions, you put a D here. And we can make the same statement, actually, if we ask for a kind of stronger type of convergence, which is not pointwise, but it's integrated mean squared error. So in fact, suppose x lives between 0 and 1. Then if I look at the integrated mean square between f hat and f naught, it's still bounded by this, under some a little bit more conditions. You can see the reference I put in the note. So this is the convergence that we get for kernel regression over this function class. This is assuming that f0 is in this function class. So you see the smoother f is, so the higher order we assume for the function class, the better rate we get. Remember with local, with kernels, k-nearest neighbors, we were kind of stuck at 2 over 2 plus d. Here we keep going up as we increase the smoothness. And the important thing to note, we'll come back to this next time, is that this is the best we can do over this function class. This is the minimax rate of convergence over that older function class. So as long as we're all comfortable with assuming our function behaves like this, kernel, or more generally local polynomial regression achieves the best rate. All right, see you on Thursday.
There you go.